Hi, welcome to another edition of Linear Algebra. Today we are going to continue our discussion about Eigen Analysis, and we are going to do 2 by 2 cases still. So I'm going to do one example where we are going to summarize what we did last time. We are going to have a shortcut for doing it quickly. I'll explain that. I hope that you take your problems and go through the full set of steps, but when you are in a rush and you want to do it quickly, that's what we are going to learn how to do that. Then we are going to take a look at some special cases and see what kind of challenges might be ahead of us. Uh, I'm going to take a look at this example, this matrix, and find its eigenvalues, eigenvectors, and eigenspaces, but we are going to do this thing in quick set of steps, unlike last time that we were going through reinventing the wheel. Actually we did invent the wheel, and then this time we are going to do it quickly. So step 1. So we are going to take a matrix M 4 minus 2 5 minus 7. So I'm going to do that problem, and then later on we are going to go on to some problems that are actually a lot easier, but somehow they get to be confusing because they're easier. Kind of sounds strange to say that, but we'll see. Okay, so here's my matrix. What do I do now? I form minus m minus lambda. Sometimes they write it m minus lambda times identity. What does that mean? It simply means that I am forming this particular matrix where the value lambda is subtracted from the diagonal only. Okay, so again, remember, we are just going through the quick set of steps, the explanation. You have to go back to the previous lecture to see what happened. Then we set determinant of m minus lambda or m minus lambda I, either way, they're the same thing. The determinant for 2 by 2 is easy, product of this diagonal minus the other one. So I write 4 minus lambda times minus 7 minus lambda, and it's a good idea to put everything in the parentheses to avoid making mistake with this minus here. Okay, then we expand this. We want to solve the equation this determinant equal to 0. So I multiply lambda times on minus lambda times minus lambda is lambda squared, and then minus 7 times minus lambda is plus 7 lambda, and then minus 4 lambda, and 4 times minus 7 is minus 28, and that one is plus 10. That is equal to 0, and then this boils down to lambda squared plus 3 lambda minus 18 equal to 0. So we always come to some creature of this sort. Now last time I forgot to mention that there is some name given to this. This is called characteristic polynomial. It plays quite a bit of a role in everything we do, and when you are looking at the equation, the whole thing all the way to that side, this is called characteristic equation. And then the solutions of it, sometimes called characteristic values, and that's same as the eigenvalues. So lots of names here. So at this stage, all of our problems are like academic type with integers, and then at this stage you most often come across problems that are easy to factor and such. We are going to keep the more difficult cases for later on. So at this stage you just factor this thing with the skill that you have from high school. You should be able to do this thing quickly. two numbers such that the product is minus 18 and the sum is 3. So you make sure you do this thing carefully. Lambda plus 6 times lambda minus 3 equal to 0. This is our factorization, and then we get our lambda equal to minus 6 and then lambda is equal to plus 3. These are our answers. And so we said one name for these things are characteristic values, which is same as what we called eigenvalues. Okay, step 1. So we found that these two, and the tradition is to go ahead, label them, and in your software, small one goes first and the bigger one goes last, and so on. So we have so far, so what we have found out so far, lambda 1 is minus 6, lambda 2 is equal to 3. These are our eigenvalues. Now on to the next stage, which is, well, what are the eigenvectors? Eigenvectors, again, the shortcut, we take this, plug it in that m minus lambda and see what we get. So I get, so what we are going to do next, finding eigenvectors. Again, I recommend that you go back to the previous lecture and see the reason for all of these steps, so that it doesn't look like just a recipe. You understand what we are doing. So I'm going to put lambda 1, so I'm going to have 4 minus 6 and then minus 2 and then 5 minus 7 minus 6. Again, I put my ingredients in parentheses so that less chance of making mistakes. So I get 10 minus 2 and 5, and this one is minus 1. You pause for a second to make sure everything's checks out so far. How do you know it checks out? The rows are proportional, or the columns are proportional. Rows are proportional. Like if you take this row and double it, you get that one. Columns are also proportional. This check is only good for 2 by 2. For bigger matrices, you have to work harder to check that you are doing right. Okay. Then you solve the following equation: 10 minus 2, 5 minus 1 times x, y equal to 0. Let's write it in traditional occasion. 10x minus 2y is equal to 0, or 5x minus y is equal to 0. It's the same thing. Okay, how do we solve this thing? Well, we have learned from beginning of semester to do Gaussian elimination and all of that stuff. We're great, but this Gaussian elimination is like elephant gun. What we are dealing with here is just a mosquito. You know, if you want to bring an elephant gun to hit a mosquito, be my guest. Sometimes you make more mistakes doing that. You might as well just swat this mosquito by hand. So these two equations are the same equation. So any of them you do will solve the other one as well. So let's pick out the easier one, a smaller number. So just pick, so I'll leave the Gaussian elimination out for a second. Okay, how do I solve this? Once I solve this, I have solved the other one as well. All you have to do is to come up with two numbers that matches this, and we said don't come up with the cheap answer. 0, 0 is not going to do any good for us. Something other than that. And well, the numbers you choose are going to be the same numbers that you see here in opposite order, in one of them made negative. So I need to figure out y and x, and it's quite common that students just get them mixed up. If my y is 5 and my x is 1, okay, x takes the number of the other one, y takes the number of the other one, and one of them has to flip the sign. Okay, so we get 1 and 5. That is the eigenvector we are looking for, 1, 5. Okay, you might say, well, I insist on Gaussian elimination. I want to make use of my elephant gun. I paid for it. I want to use it. What do I do? So you say y is a free parameter. Y is equal to t. Okay, y is a free parameter. Then 5x will be equal to y, which is equal to t. So x is equal to t over 5. So xy is t over 5 and t. Factor your t. That's what we did beginning of a semester when we were solving this. Okay, any t is good. Just to make our life easier, we go after the common denominator of these things, pick the smaller positive thing. So t equal to 5, I can choose t to be any number. So I choose t equal to 5 so that when I multiply, I get friendly numbers. So I get, if this is 5 times 1/5 in 1, so I get 1 and 5, which look, that's just what we had over there. So we can go after the concept of a free parameter and then backward solution and get the back substitution, get the x, get the set of all possible eigenvectors and choose one from this listing. Okay, so that was the elephant gun, and here was just handle mosquito yourself. This is easy to solve. Just double check, make sure you don't make a mistake, you don't put the wrong number and so on. So what we have here is, if lambda 1 is equal to -6, we might as well call that with also subscript number 1. No, you might say, well, why are you taking t equal to 5? Take anything you want other than 0. 6, 7, 10. 10 would be nice. 10 here gives you 2 and 10. Take t equal to 15, you get 3 and 15. But you could take fractional numbers as well. We're just going after whole numbers. It's just easy to work with and less error prone. So Eigenspace then. What's the Eigenspace? Is the line that just lines up with this. So if this is 1, I have to go 1, 2, 3, 4, and 5. It's kind of squished here, but okay, that entire line, the entire line, including the 0. Now we don't exclude 0 because it's going to create a hole over there for no good reason. So that's going to be our Eigenspace. Okay, now can I imagine that you're going to go ahead and do the next one before I do it, huh? Just go ahead and duplicate all of this set of steps for the next eigenvalue, the bigger one, and get your eigenvector and then eigenspace, and then you're all done. Okay, so let me bring up our clue here to entice you. That nice waterfall. Okay, so you're gonna go ahead and then do this one by yourself. Pause this thing and then come back. So now I go after next round. So next round. So what's the idea? The idea is that we take m minus lambda. In that we plug what lambda we got. So it's 4 minus 3 now, then minus 2, 5 minus 7, and then minus 3. We clean this up. I get 1 minus 2, 5 minus 10. Is that right? What was our check? Does this thing check? You remember the check? What do we do? So what this is 5 times that, or this column is minus 2i that. If that checks like that, we are done for that step. So again, that's only good for 2 by 2. When you go bigger matrices, the check itself is going to take a while. Okay, and then what? We take this and solve the following equation with it. 1 minus 2, 5 minus 10. So times xy. This is sometimes referred to a null vector. Null vector, so this thing, it has a name, everything has a name. This is sometimes called the null vector of this matrix, whatever is sitting next to it. Null means when I multiply it, it nullifies it, it gives me a 0. Null vector means when you multiply by matrix, it just gives you 0 out. Typically, null vector itself would be just 0, but because this is a special coming from that special number, we have other choices. What other choices we have? Let's multiply it out. So again, I have x minus 2y is equal to 0 and 5x minus 10y equal to 0. Once again, this is a system. How do you solve it? We had that entire machinery at the beginning of a semester, and we had this very nice thing here to help us when the going gets tough. But well, now the going is not tough. In fact, if you bring it into this, it probably becomes harder. So just look at this two equations. They are essentially same equation. Solve one of them. Yeah, well, pick the easier one. And what are two numbers that if you put here will make it true? Again, cheap answer is not accepted. So what is it? If I take y equal to 1, x equal to 2, that's the easiest set of numbers I can find. Quickly check that you're not fooling yourself. Signs, everything is working out. And here is the answer. 2, 1 is our second eigenvector. Again, you can go take y to be t, and then so you can take y to be t. If you want to do it the hard way, x becomes 2t, and then your xy becomes 2t and t, and then you factor the t. What's the easiest t to use? Easiest t to use, well, I don't have any fraction to get rid of. I'm not allowed to use 0. Easiest t to use is 1, and 1 times 2, 1 is just 2, 1. So we are handling this thing also quickly. If lambda 2 is equal to 3, well, for lambda 2 equal to 3, v2 became 2, 1. The picture of that is, okay, you go 2 and the 1. This is the Eigenspace. Eigenvector, the one we are selling, is this one. Of course, if you double it, triple it, or multiply by anything other than 0, that's still good. So this is a representative of an entire class of eigenvectors, and eigenspace is this nice line that is our Eigenspace. So Eigenspace, you can draw it like that. You can also say, you can also talk about it as this answer, t times 2, 1. That it means pick all possible values of t. Now t equal to 0 is also thrown into the mix. That's the eigenspace. Here, eigenspace, I can write it as this one or a multiple of that one. That's more attractive. It's all the same. So I can write it t times 1, 5. So you notice that we can always multiply this vector by any number, and we are still fine. There's nothing illegal about it. Okay, and in most of the homeworks, they want you to put these two pictures together. It's one single picture and 2 lines on it, and then that would be the set of eigenspaces. So on the homework, you're going to see the following. You're going to see this is one, and then that's the other one. The 2 eigenspaces are thrown in at the same time. Okay, so we solve this thing, and so most of the problems we are going to look at are going to be of that type. Now, notice a crucial step in this deal was solving this characteristic equation. You remember from high school, you probably solved thousands of these things. You remember there were three possible scenarios there. Most of the problem you solve follows this scenario, but well, there were others. Now these special cases are gonna some of them follow the other cases that you have from quadratic equation, and then we have subclasses of those that are also coming up. We're going to take a look at that. Okay, as I said, these simple cases with lots of zeros and special numbers and such are kind of easier to recognize ahead of time before we fall into this machinery. This machinery is going to become a bit confusing because pretty much everything kind of disappears and you have like lots of zeros in front of you, and typically students get confused as to what's going on. But before we just duplicate these things, maybe it's going to be easier for us to just look at it and recognize what the answer is, and then go back and actually duplicate it like that. Special case number 1, I have 3003. You recognize that it's just 3 times the identity. When we go find out the eigenvalues are just going to be these two numbers. Peculiar thing is going to happen. When we try to find the eigenvector, everything becomes eigenvector. Meaning you don't have to even look. Whatever you pick is going to be an eigenvector. So that's going to be a new situation for us. Instead of these cases where we have all of our eigenvectors sitting on special lines, in this case there is nothing special about any line. All of them are good, and your eigenspace becomes the entire plane or entire R2. This is kind of easy to see. Let's see. So again, we are trying not to fall into the trap of all the machinery. You just see, if I have 3300, what do you get if you multiply by some vector? Let me pick some vector. So I don't give it a name. I don't give it a number. Just put it A, B. So that means any vector. It can be any vector. So multiply 30 with A, B. What do you get? You get 3A. Is that right? And 0. Well, let me write it. 0B. 0A plus 3B. Well, any civilized person is going to clean this up. It's going to write 3A, 3B. And that civilized person is going to see, well, this is just 3 times whatever I had to begin with. Okay, if the output is a multiple of the input, you got yourself an eigenvector. But now, we didn't work any hard, make any specification as to who's A and who's B. It doesn't matter who's A and who's B. It always turns out to be tripled. So AB, any AB. So any AB. Now we put a little fine print here. We put a fine print like as we have to say it quickly or make it very small. Other than 0. Okay. For that technicality, we're gonna go say don't bring this guy in. Okay. Any AB is an eigenvector. Well, you might say, duh, of course. This is essentially same as number 3. If you multiply by anything, well, it's going to triple. Okay, 3 times the identity. If I have a matrix made out of a number times an identity, is going to act like just multiplying by that number. So it's not a big mystery that every vector becomes an eigenvector, because 3 times any vector, well, is 3 times that vector. Yeah, so it's an eigenvector. Okay. Then comes up the issue of, well, if you want to hand somebody the eigenvectors, what are you going to do? We are going to give them a representative set that everybody else can be made out of those. It's called the basis linearly independent basis. So here's the easiest thing to use. So I choose one of them to be lining up along the x-axis, the other one I line it up along the y-axis, but I had many other choices to make, so it's just a lot easier to say my eigenvectors, I choose one of them to look like this, I choose the other one to look like that, so everything is just nicely set with lots of interesting easy properties to diagnose and so on. But pretty much any other two, so long as they're not proportional to each other, would have done the same job for us. So that becomes our so these are our eigenvectors, my eigenvectors. Eigenvalue, there is just 3. Since there have to be always as many eigenvalues as the size of the matrix, you just have to duplicate it, like 3 and 3. That's like your eigenvalues are these things. Well, now, how about the eigenspace? Eigenspace is all of these, okay? All of the vectors that triple are thrown, all of them together, into your eigenspace. And now we don't just sit on the axis or any two lines or something. We say, well, color everything. I guess Van Gogh like yellow, so we go with yellow. So eigenspace is the set of all the vectors that have that eigenvalue, and all of them includes this, and that fine print doesn't apply here. We do include the 0. Okay, so that was easy. Now, of course, see what happens when we try to do the official way. Official way. So, okay, going the standard method. See if we're gonna be able to swallow this. So, standard method was to take the matrix that we had, subtract lambda from the diagonal of it, and figure out the determinant of that and set it equal to 0. Okay, that was our step. Like here, we subtract lambda, make the determinant, set the determinant equal to 0, and simplify. So this times this minus this times that. Well, that's not bad. 3 minus lambda times 3 minus lambda, and the other way is 0 times 0. Well, multiply it out. 3 minus lambda times 3 minus lambda, and this is 0. I don't need that. Well, I said multiply it out, but that was actually silly. Why multiply it out? You can get your solution right here before you multiply anything. Either first factor is 0 or the second factor is 0. It's already factored for you. Why bother to duplicate your work? So here are my two answers, 3 and 3. So the way this is different to get going, the way it's different is that in this case we had two different numbers, and then here we have identical numbers. Whenever solutions in a math problem becomes a set of identical numbers, we should expect a headache coming up, or interesting depending on point of view. It's like that movie reminds me of something called Parent Trap. It's like if you have twins, if you have got twins, you got trouble. Is that right? Twins means trouble. By the way, you don't say I have one root, that's just 3. You know, if you have twins, you don't say I have one kid because they look like each other. It's a lot worse than just one kid. With the two of them. Here also in mathematics, you have got identical roots, you got problems coming up. We're going to see later on. So I take one of these, well, either one that you pick, and you put it here. What happens? 0, 0, 0, 0. Well, none of the problems you have dealt with, and everything being 0. But, well, that's what it is. So what are we doing? We are at this stage. We had a matrix times x, y equal to 0. So I'm trying to solve this. Well, write it out. 0x plus 0y is equal to 0. 0x plus 0y is equal to 0. Well, didn't I tell you get confused? What is that? Well, simple. Y can be anything. X can be anything. So if you want to go to the official way, y is some parameter, as x can be any parameter, doesn't have to be that. So y is arbitrary, x is arbitrary. So I have x, y. This is s and t. First time we have two parameters here. I can write this thing as S0. Remember from the beginning of semester we had some funny steps like that. We separate oil and water. We separate S's and T's. Now from this one I can factor S. From this one I can factor T. So my eigenvector is any multiple of 1, 0 plus any multiple of 0, 1. So I'm gonna sell these two as my eigenvectors. 1, 0 and 0, 1. These are the eigenvectors. I could have done any particular s and t, make one, and some other s and t, make another one, and just make sure they're not multiples of each other, and then I'll be set. But why go through such a long ways? This is just as good as anything. So this is my set of eigenvectors. These are my eigenvalues. And how about my eigenspace? Well, eigenspace, all these possible s's and t's, all of them. What is that? All of them. Well, it's just R2, it's the entire page. So eigenspace is, you can write it R2, you can write it set S and T arbitrary, or many other ways of referring to it. Okay, so if this method confuses you, as I said before, from experience, I know that when students see all zeros everywhere, they kind of lose the handle by which you recognize the stuff. Like in this problem, okay, you have some numbers to look at and then come up with some specific answer like that. Here, what's happening is that, well, all of those landmarks are gone, and you kind of get uneasy. Well, what is this thing? And it's just not bad, especially for those of you going to mathematics. You have to kind of get used to these extreme cases. Let's go to the next example and do that quickly. So 3, 5, 0, 0. That is, so I have another matrix M, 3, 0, 0, 5. So M minus lambda. I'm going to gradually speed up and not to say all the steps. Determinant of this, these two, those two. Well, the other product of the other two is just 0. I don't have anything there to worry about. I don't go ahead and multiply them, because then I have to factor it. That's going to be silly to multiply and then factor again. You'll be back where you are. So here we just say lambda equal to 3 is one answer, and lambda is equal to 5 is the second answer, which is essentially, if those of you want to memorize, I don't want to recommend that. It's just the numbers on the diagonal. If your matrix is has a triangular shape, here is a little trick. If I have a matrix triangular shape, the eigenvalues are just these numbers. So here I'm giving you some little pointer for doing some of these problems quickly. If your triangle is if your matrix is triangular, the numbers on the diagonal are just your eigenvalues. You don't need to go through all of that step. Anyway, lambda is 3, lambda is equal to 5. Now I go ahead, so we say number them 1 and 2, so lambda of 1 is equal to 3. What do I do next step? Take this number and plug it here. So what do I get? Here's still a bit confusing because on the first row you don't have, so lambda equal to 3, we plant it here and that is what we get. Let's see if we can handle ourselves here and not get confused. So I have to take this thing, multiply by any vector and make 0 out of it. First row, just read 0x 0y is equal to 0. That doesn't tell me anything. Next says 0x plus 2y is equal to 0. Well, this is 0. 2y has to be equal to 0, so that means y has to be 0, which then tells you if y is 0, x now becomes arbitrary. X becomes arbitrary. Arbitrary means what? Arbitrary means the parameter t. So your x, y, my answer becomes any number and 0. And if I factor my t, so eigenvector corresponding to 3 is 0, 1. Let me see if I can entice you to do the other one. So lambda 2 is equal to 5. Okay, so here is your Q. That's your Q. Finish the problem and come back. Okay, no cheating. Pause this thing, finish, come back. Now what? Take so you did pause, is that right? 5, I plug it here. 3 minus 5 becomes minus 2, 0, 0, and this is 0. Okay, let's color this thing differently. So I took 5, put it here, and this is what I got. To figure out what is the eigenvector, we find the null vector of this matrix. What is that? Minus 2x plus 0y is equal to 0. 0x plus 0y is equal to 0. Well, from the first equation we realize x has to be some parameter. Excuse me, x has to be 0. I made a mistake myself. X has to be 0. Y can be any parameter, t or s or anything. T. So x, y now becomes 0t. And you can factor a t becomes 0, 1. Here's my v2 that goes with this one, 0, 1. These two go together, these two go together. How about Eigen Space? Eigen Space, all of these is the Eigen Space. T times 0, 1, who is that? T times 0, 1 is all of this. And here, this is the other eigenspace. The eigenspace of this is all the vectors that line up here. Now we are all done. Again, in typical problem, these two are going to be on the same picture. Okay, so that was another special case. For third, and perhaps the most offending, if you want to call it that, is going to be this one. They're not going to call it offensive, they're going to call it even worse. They're going to call it defective. So imagine choosing a pejorative name for a matrix, but that's how it goes. This is called defective. What is defective about the matrix? It's just a good set of numbers. Why do you call it defective? So I take M3, what's that? Doesn't matter what number I had, but let me make sure I have the same thing. 3203. Okay. What is defective about this thing? Peculiar thing is going to happen. One of our eigenvectors is going to go AWOL. It's going to become missing. We are just going to have one eigenvector. And in mathematics, that's hot headline news. Is like breaking news. To use looks like, well, it's just another set of numbers. For us on the other side of the line, this is like, okay, all the cable channels should announce that something happened here. Well, what happened? First of all, m minus lambda, that is 3 minus lambda 2, 0, 3 minus lambda. Maybe we should call it the eigenvector alert. There have alerts for everything these days. Eigenvector alert, yes. So, well, we take a determinant of that. Determinant of this 3 minus lambda times 3 minus lambda minus 2 times 0 is equal to 0. Again, this is just 0. That makes our life easier. And we don't bother to multiply, because you multiply, well, then you have to factor, and that's going to be silly. So lambda 1 is equal to 3, and lambda 2 is equal to 3. So I still, just like what I said, if you have triangular shape matrix who are sitting on the diagonal, that's your eigenvectors, all of them. So long as bottom is all 0 or the top is all 0, that rule does apply. Now what about it? I take this, well, whichever of them you pick, and put it in that matrix. What do I get? I get 0, 2, 0, 0. Okay. Multiply by x, y. We find the null matrix of that. What does my equation lead right? 0x plus 2y is equal to 0. And second equation, just like what we had before, and that's 0. Okay, the first equation tells us y is 0. Second equation tells us x is arbitrary. X is arbitrary. So my eigenvector becomes an arbitrary number and a 0 number. Well, that's just t times 1, 0. Okay, you say, I found one eigenvector. Okay, how about the other one? Well, look, is how silly it's going to look if you put, say, I put the other 3. Well, the 3 is the 3. Whatever you put, that's what you're going to get. And then you cannot say I have eigenvector 1, 0, and the other one is just 1, 0, or say 2, 0, or whatever. Your eigenvectors that you dish out, they have to be linearly independent from each other. Is that right? It's not like we can paint it different color and sell the 1, 0 as some different eigenvector. Here's a big strange headline news. There is only one eigenvector for this matrix. So they share just one eigenvector. When we have less eigenvectors than we expect, okay, this size 2 by 2, we have less than 2 eigenvectors, we call the matrix defective. This matrix is defective. So we gave it a name. Maybe we should call it luxurious or something like that to not have a negative, but something is missing. Yeah, they call it defective. Okay, then more terminology is going to come up on this thing later on. So let me just mention it here so that it would be a good practice. When a root repeats itself, we say it's just like giving birth to multiple kids at the same time. We use a similar terminology. So we are going to call this thing 3 is a root of multiplicity 2. meaning happens twice. So this is a root of multiplicity 2. I don't know if you remember Octomom. She had 8 kids, so that multiplicity would have been 8. Now multiplicity is 2. This is referred to as geometric multiplicity. Actually, sorry, I made a mistake. This is algebraic Geometric multiplicity refers to how many eigenvectors, linearly independent eigenvectors you found. So that's called geometric multiplicity. One. So geometric multiplicity is at most equal to that, is at least 1. If it is less than 1, then that matrix is defective. How about these other cases? Well, this one just had one baby, and then that was another baby like some other time, and then these are algebraic multiplicity 1 and geometric multiplicity 1. So naming this thing, it is going to be algebraic multiplicity is 1, meaning when you are factoring it, that factor shows up just once. So the number of times a particular factor shows up in the algebra is called algebraic multiplicity. How many eigenvectors do you find for it? That's going to be called geometric, like it has to do with its geometrical picture or something. So it's called geometric multiplicity. Well, cannot be anything other than 1 anyway. The same thing here. So again, this is algebraic multiplicity is 1, meaning there is only one such factor there. 5 shows up just one place, and you only find one vector here, so you call it geometric multiplicity is also 1. Let's go back up here. How about this funny situation, 33? Well, let's come back down here. You see the factor showing up twice. What does that tell us? That tells us, well, you see it here. This is algebraic multiplicity is 2. It shows up twice. And then for that eigenvector, we have for that eigenvalue, we have 2 eigenvectors. So in this case, geometric multiplicity is also 2. Okay, it becomes a little bit technical here. It goes towards some major theorem, counting of all sorts of eigenvectors you are going to have, and so on and so forth. For those of you headed toward mathematics, called Jordan normal form theorem. So we have a Jordan too. You guys have a Jordan. We have a Jordan. Jordan normal form theorem. But here here's the gist of it as to what happens if you have a big matrix, lots of eigenvalues. They can have various multiplicities, and then there's going to be geometric multiplicity, which is somewhere between 1 and your algebraic multiplicity, and so on and so forth. Okay, let's not go down that rabbit hole. So here's the idea. We learn, what happened here? We learned a shortcut. How do we do this? Okay, that's the meat of the issue, is that one. I want to make sure everybody is up to speed with respect to these. And then we have a bunch of special cases. I haven't exhausted all the special cases, just some of the easier ones. There are special cases that are harder than these. I just mentioned some. So let's just go ahead and take a look at this thing one more time. and then I mention a few more words about special cases, perhaps for the next lecture or something. So matrix, subtract lambda from the diagonal, multiply in a cross pattern and subtract equal to 0, clean up, make sure your algebra is done right. You get an equation just like equation back in high school. Has a name though. The side's called characteristic polynomial. As the equation is called characteristic equation. You solve it, it's called characteristic roots or characteristic values. So let me see, let me also put this one here. Character is the roots that you're finding, characteristic roots. Same as eigenvalues. You find two of them, smaller one, larger one. That's how they get labeled. You start with the smaller one, plug it here into your equation, clean up. Here's your check. Your rows and columns should be proportional. Then you find the null vector of that. That is, what should I multiply it with so that I get 0? You get a so-called homogeneous system. These are baby ones, so you solve it by inspection and make sure you did it right. So for your eigenvalue, you find an eigenvector. If you want to do it a long way, or if you want to prepare for, what was it that we had here? By 2 lectures from now, problems are going to be big enough that doing it here might be beneficial. But right now, these are small ones. Okay? And then you find your your eigenspaces. I guess if I lose my voice, it means you're getting tired of me. So when we looked at some special cases, other special cases, well, what if this equation you get is nastier than what you did here? What is the case we didn't cover? When you have complex roots. So with complex roots, you have to learn complex numbers, all of that fun, and we cannot ignore that issue either. Let me put that for another day. So until next lecture, good luck and God bless.